Okay, so the topic that we are going to start in today's lecture is theory of numbers. As you already know, this course actually is a collection of multiple of fundamental topics, basic topics from mathematics, mostly algebra. One of the most important of those topics is theory of numbers, and we are covering this topic following the book by Bernard and Child. As I have already discussed earlier, that most of the topics we're going to cover in this course are going to be from Bernard and Child. Theory of numbers, actually, some of you are already experienced with theory of numbers, but some of you may not actually recognize the topic. So, in short, theory of numbers is actually a study of numbers, and we know different kinds of numbers, right? We know real numbers, complex numbers, etc. But this particular topic is limited to integers only. When we say theory of numbers, we do not mean theory of all numbers, but only integers, or sometimes called whole numbers. Now, in any standard textbook on theory of numbers, the first topic that they start with generally is the division algorithm. What is the division algorithm? It's pretty simple, actually. Say, for example, you have a number 8, and you are trying to divide the number by 3. So if 8 is divided by 3, we get a remainder of 2, and the quotient is 2. Both of them are 2, basically. 3 2s are 6, 6 and 2, 8. So when divide 8 by 3, the remainder is 2. And one could write 8 is just 3 times 1 plus 5. This statement here is correct, but we do not call this a remainder. This is not a remainder because generally we expect that the remainder is going to be less than the divisor, right? So if any number a is attempt to be divided by b, then the structure is we get a quotient q and possibly a remainder r, and r is in the interval 0 to, it should be less than b, but it's not necessarily strictly greater than 0. Sometimes we can divide a number by another number completely. In those cases, there is no remainder. So in such cases, r is equal to 0. So r can be 0 and anything greater than 0, but not exceeding or equal to the divisor. That is why we do not accept this situation, even though this is correct in terms of finding the remainder, but we accept this situation because this qualifies. So in that sense, you can also see that 8 could be written as 3 times 3 minus 1. Now, 1 is within this interval. In our case, b is actually 3, right? B is actually 3 and a is 8. So 1 is less than 3, but we have a minus sign here. This is not also acceptable according to the definition, because r cannot be less than 0. So even though this is also a situation where everything is correct mathematically, and the magnitude of the remainder also satisfies the condition, but the sign is negative, that is why we also reject this idea. So in that sense, the pair q and r becomes unique. for any pair A and B. You can see that. Since we are rejecting these cases, the condition on R actually means that we can get a unique pair of Q and R for every AB. And the fact that we can get a unique pair of Q and R for every AB is actually called the division algorithm. So the formal statement goes like this. If you are given a pair A, B, for all pair AB, of course, I'm not explicitly mentioning, but all of them are integers because we are not going to deal with non-integers, right? And technically, in this particular case, we are actually dealing with positive integers also. So let's write z plus here. And generally, the convention is writing the plus as a subscript. So we are dealing with positive integers. So if you are given a pair of positive integers A and B, then you should be able to find another pair of positive integers Q and R such that A can be written as BQ plus R, and this pair is actually unique. This is the overall statement of the division algorithm. Now, there are basically some additional facts that you can extract from this particular algorithm or this particular, let's call those facts theorems. So there are some theorems on division. So next comes theorems on division. The first one is, these are pretty basic actually, to be honest. The first one is, if A divides C and B, actually I wrote, if C divides A and C divides B, this symbol is read as divides, all right? It means A is divisible by C and B is divisible by C. Then we must have C divides A plus B. And this should be pretty straightforward to prove, right? Because if C divides A, you can write A as an integer multiple of C, right? So A can be something like K1, KC. Also, C divides B means B can be written as some L times C, where K and L are, of course, integers. Otherwise, we didn't call it divides. Okay. So then you can understand that A plus B is simply excuse me. A plus B then becomes KC plus LC. So just take the C as common, factored out, So you can see that A plus B is also a multiple of C. Now, if this is clear to you, okay, throughout my lecture, if there is any kind of confusion anywhere, if you have any kind of doubt, please stop me and ask questions, all right? So if this is clear to you, it should also be clear to you that I can just write a minus sign here and say that C divides the difference of A and B also. Because the only change that's going to happen in the proof is just in this symbol here. And you can just replace all the plus signs by minus signs, and the proof remains same. And while walking through the proof, you should also have realized that if I just wrote some m here and some n here, that wouldn't matter either. In those cases, you just add the m here as a coefficient and add the n here as a coefficient. Then you could factor out the c in that case or as well. Just the coefficient here would become something like km plus ln. But the coefficient doesn't matter. All that matters is you could take the c factored out, which means c divides this combination of a and b also. We call things like this a linear combination. Something like k1 x plus k2 y. Okay. K1 x plus k2 y. Things like these are called linear combination of x and y. Now, you can see that this m and n are actually integers. So in this particular case, we can call this integer linear combination of the integers a and b. So the main idea is this: if c divides not just two, but a number of, if c divides some numbers, then c should or c must divide any integer linear combination of those integers, right? So this can be generalized to cases where you have more than two integers. Okay. Another idea is if you divide a by b and eventually find out that r is the remainder, then if you were to divide CA by CB, you would get a remainder CR, and literally the same quotient. And while describing the fact, I already proved it. It was that straightforward, right? I just multiplied the both side of this equation by C, and the new equation reads like this: if you attempt to divide CA by CB, CR is the remainder that you are going to get, and the quotient remains same. Um, now, what could we say something similar? Or I mean something similar, but instead of multiplying, we want to just divide. So divide A by C, B by C, R by C. I mean, could we say something similar for division as well? That is, if R is the remainder, when A is divided by B, then R by C should be the remainder when A by C is divided by B by C. For this to hold, there is a condition you should be able to understand already, is that for this to hold, C must divide A and C must divide B, because otherwise, if this was not true, then A by C and B by C were not going to be both integers, and in that case, it wouldn't make any sense. There is no point in talking about remainders when you are dividing 1.2 by 0.7, right? The concept of remainder is useless when you try to divide by some non-integer by some other non-integer. That's the idea. Okay. And you know that if A and B are both divisible by C, then the remainder is going to be divisible by C as well. Otherwise, you can prove that if you just write A by C is equal to B by C cube plus some remainder which we don't know anything about, for example, then just change the side to write r prime equals to a by c minus b by c q. Now, you can see that if this guy is integer, this guy is integer, and this guy is integer, r prime is going to be integer as well. In in that in that case, this r by c has to be an integer, which means r has to be divisible by c as well. So in other words, in short, we can say that if a and b are divisible by c, r is going to be divisible by c as well. Okay, next is the next idea is most of you are already familiar with, I guess, the greatest common divisor. Now, the I mean, what is a greatest common divisor? First of all, what is a common divisor? If you have two numbers a and b, then there could be some common divisors of a and b. That is, there could be numbers that divides both a and b. And among those common divisors, there has to be someone who is the greatest, because the divisor cannot exceed the divisors of a and b cannot exceed the guy who is the minimum among these two, right? If you have two numbers 5 and 12, divisors of 5 and 12 cannot be greater than, common divisors of 5 and 12 cannot be greater than 5. So otherwise that number would not be able to divide 5. So there is an upper bound for the set of common divisors of any two number, right? So that guy is called the greatest common divisor. Now we have some theorems related to greatest common divisor or common divisor. First of all, please turn off your video. All of the students should turn off their video and audio unless they want to discuss something with me. Okay, so the first idea, the theorem that we are going to mention is, if R is the remainder when A is divided by B, then common divisor of AB is equal to common divisor of, okay, my handwriting is bad in general. Today it's exceptionally bad. Okay. So common divisor of A and B and common divisor of B and R are exactly same. May sound surprising to some of you, but it's actually easy. It's very easy to prove, because if R is the remainder when you divide A by B, then A must have an expression something like this according to the division algorithm, and this Q and R is unique, right? Now, from this equation, make R the subject We actually did something like this in our last page. All right, so this is using of ideas. Uh, if there exists some common divisor or some integer that divides both a and b, then we can just factor that common guy out and conclude that that guy is also a divisor of r. So if C divides A and C divides B, you can conclude that C must divide R as well. And we already know that C divides B. This is just writing the same known idea again. May look redundant, but it is going to be useful. You will see later. So common divisor of A and B and common divisor of R and B are same. And we can use this particular fact to find out the GCD of two numbers. Some call it the Euclid algorithm because it was by Euclid. For example, if this is actually this can be mentioned as the theorem number 2 on the greatest common divisor. So maybe you want to find the greatest common divisor, sometimes written in short as GCD of A and B. And GCD of A and B has even a shorter version as a name, A comma B in first bracket. Do not confuse it with open interval. Basically, the meaning depends on context. We are not dealing with anything like intervals, right? We are dealing with integers. So there is no interval. So finding GCD of AB, or just GCD of AB in short, how do we do that? You have A, B, Q plus R. Let's call this guy Q1 and this guy R1. Now, what we can do is take this B and divide this B by R1. You are going to get some other quotient Q2 and some other remainder, possibly R2. And repeat this process. So take this R1 and divide by R2. Get some quotient Q3 and some remainder R3, and keep repeating. So technically, the sequences of numbers on the left-hand side are A, B, R1. So let's write another case just to make it a bit more visible. Take R2 divided by R3. You have quotient Q4 and remainder R4, and keep going. Now the sequence B, R1, R2, etc. Can you see that this is a strictly decreasing sequence? Because by definition, R1 has magnitude, not just magnitude. R1 is a positive number, B is a positive number. So Euclid's algorithm tells us that R1 is actually less than B. So R1 is less than B here. From similar logic, R2 is less than R1 here, because remainder is not going to exceed the divisor, right? And here we must have R3 greater than R2, I mean less than R2, and so on. So B is greater than R1, R1 is greater than R2, and we have a strictly decreasing sequence. Now, any subset of taken from the set of positive integers has a lower bound for sure, because these are positive integers. They cannot overtake 0 if we keep decreasing them. So at some point, you are going to get, this cannot go indefinitely because we are dealing with finite numbers. We started with a finite number A and a finite number B. So you cannot just keep going indefinitely. So at some point, you have to end. and it's going to end with a 0, right? So at the point where you get this 0, for example, that point is at some point you are going to get Rn minus 2 equals to Rn minus 1, Qn, Qn plus Rn. And maybe in the next step, when you are trying to divide Rn minus 1 by Rn, get a quotient Qn plus 1. And maybe now this is the step. I have not mentioned any specific n, so this is generalized situation. So for some particular value of n, at some point you are eventually going to get a 0. Let us consider that 0 is technically we were to write Rn plus 1 here, so that Rn plus 1 is 0 after the nth step. In that case, the GCD, my claim is the GCD is Rn. Let's see why. GCD of A and B is Rn. Now, as we have mentioned, let's use this notation stands for greatest common divisor. And there is another symbol. This stands for least common multiple. These are standard notations. So I'm going to use a non-standard definition here just for the sake of simplicity of writing. Let's call this just a common divisor of A and B. Let's define like this. This stands for common divisor of AB, which may or may not be the greatest. So this is not necessarily greatest common divisor. Now, common divisor of A and B, according to the theorem we mentioned in the last page, should be equal to common divisor of B and R1. And common divisor of B and R1 should be from this equation, of course. The common divisor of B and R1 should be common divisor of R1 and R2. You can keep going like this. Common divisor of R1 and R2 should be common divisor of R2 and R3. And finally, at some point, common divisor of, they are all going to be equal. And at some point, you are going to get Rn minus 1, Rn. So technically, technically, if you consider this guy, the first guy in the pair of numbers, then you have a decreasing sequence of numbers. Let's define an order relation for this symbol. I mean that this guy is greater than this guy, just by the sense that A is greater than B. I mean, the first guy of this second bracket is greater than first guy of this second. In that sense, we have a decreasing sequence. Now, among all these common divisors, there is one case where we actually know who the common divisor is, and that is the last case. Can anyone tell me what the common divisor of these two? Okay. Concentrate on this equation. Let me rewrite the equation. Rn minus 1 is equals to Rn times Qn plus 1. Now you can see that Rn minus 1 is already a multiple of Rn. If you have two numbers, for example, 12 and 4, where one is a direct integer multiple of another, then what is the greatest common divisor of these two? They can have multiple common divisors, but what is the greatest among them?
4.
4, exactly. So we have a similar situation here. We have Rn minus 1 and Rn, where Rn minus 1 is a direct multiple of Rn. So they may have other common divisors as well, but there is a guaranteed common divisor Rn, and which is the greatest for these two particular guys. Now, basically, this chain of equation is true for any common divisor. Start with any common divisor between A and B. Those common divisor are going to divide B and R1 as well, and then R1 and R2 as well, etc., 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 so on. So any common divisor of any of the guys in this chain is going to be a common divisor of other guys as well. So let's concentrate on the last one. We have not just a common divisor, but the greatest common divisor of the last two, and that guy is Rn. So this must be the greatest common divisor of the first guy as well. So Rn must be the greatest common divisor of A and B as well. This is my conclusion. That was my claim. So technically speaking, what we just proved here is, if you have a number, for example, 12, and another number, say for example, 30, and if you were trying to find the common divisor of these two guys, what's happened is divide 30 by 12. The quotient is 2. Okay, let me use some other number than 30. For example, let's use 33. All right. So so if you divide 33 by 12, you twice of 12 is just 24, and you get 9 as a remainder. So in the last page, what we did is divide the divisor of the last iteration by the remainder of the last iteration. That was the thing we are repeatedly doing, right? We are going to divide the divisor of the last iteration, which is 12 here, and divided by the remainder of the last equation, which is 9. So divide 12 by 9, you get 3, and repeat the process. So divide 9 now by the last remainder 3. So divide 9 by 3, and at some point you were to get a 0 as a remainder. The discussion in our last page suggests that in the step where you get a 0, the divisor is the GCD. So the step that in which we got a 0 is this step, and the divisor of that step is 3. So 3 must be GCD of 12 and 33. This is how this algorithm works. Please let me know if there is any confusion anywhere.
এটাকে তো ইউক্লিডীয় পদ্ধতি বলে, রাইট?
Yes, this is called Euclidean algorithm for finding GCD. All right, let's move on. Now, there are some other facts about GCD as well. For example, if GCD of A and B is C, then what should be the GCD of MA and MB? Unless otherwise mentioned, every symbol I write here is an integer, right? M is also an integer. So we are multiplying the initial two numbers by a same integer multiple M. And if you try to find out the GCD of these new two guys, is simply going to be MC, right? So this is also a straightforward fact. Okay, these are the ideas related to greatest common divisor that we were going to cover in today's class. The next topic we are going to start, that belongs to theory of numbers, is prime numbers. And before that, I mean, there are two closely related ideas. One is prime numbers, and the other one is numbers that are prime to each other. The latter is sometimes called co-prime numbers. I think you guys know the definition of both of these two. Prime numbers are numbers, positive integers which have just two divisors, the number itself and one, and no other, right? So that means 2, 3, 5, etc. prime numbers. And numbers which are co-prime to each other means if you are given two numbers and their GCD is 1, we call them co-prime. So A and B are prime to each other if the GCD of A and B is simply 1. It would mean that they do not share any common multiple. So in that sense, 12 and 57, not 57, but 49. None of these two are prime numbers, but they do not share any common multiples. So we are going to call them co-prime or prime to each other. So 12 and 49 are prime to each other, even though none of them is a prime number. So these are the two ideas. And of course, after defining any new term, there is going to be a bunch of theorems or lemmas are going to follow. And here's one. If M divides AB and M is co-prime to any of A or B, without loss of generality, let's choose M is co-prime with 1, then this would mean M divides B, which should be straightforward to visualize, right? So if you have a number, say 3, and it divides 9 times 5. Now, if 3 is co-prime to 5, then since 3 divides 9 into 5, it would mean 9 into 5 by 3 is an integer. So 3 has to cancel at least one of A or B. But since 3 and 5 are co-prime, 3 cannot cancel 5. So 9 must contain at least one factor 3, so that 3 and the 3 in the denominator gets cancelled by each other. So this is the idea. So this would just mean, along with consideration of the fact that 3 and 5 are co-prime, this would just mean 3 must divide 9. And this is the idea. Another is if A divides N, B divides N, can you conclude that AB divides N? Can anyone tell me? If A and B both divides N, can we conclude that the product of A and B also divide N? For example, 3 divides, say for example, 105. And okay, let's choose an easier example. So 3 divides 30 and 5 divides 30. And you can clearly see that 3 times 5, which is 15, this also divides 30. So observing this example, can we just conclude that this is going to happen every time? Not really. You could actually manage to find counter examples. For example, 3 divides not okay. In fact, we can reuse this example written inside the green. 3 divides 30 and 15 divides 30. Should this mean 3 times 15, which is 45, also divides 30? This is not true, right? So why was the uppercase true but the lowercase is not? It's because in the uppercase 3 and 5 are co-primes, so they did not have any mutual interaction while dividing 30. So put 30 in numerator, put 3 here, 3 divides 30, put 5 here, 5 divides 30. So both of them individually divide 30 and they do not share any common multiple. They should also divide 30 because they are canceling different factors of 30. But when you are trying to argue similarly for the situation below, 3 divides 30, 15 divides 30, but when 3 divides 30, 30 is actually 3 times 10, right? So when 3 divides 30, 3 divides this 3. And when 15 divides 30, 15 divides, let's write 10 as 2 into 5. So when 15 divides 30, 15 actually uses the same 3 and this 5. So the 3 is using, in both cases, two different numbers cannot divide the same factor of the numerator, right? So this is the reason why the case here was not true. So we have to add another condition that A and B has to be co-prime. And if that's true, then we can safely conclude that AB divides N. You can prove, I showed by example, but you can prove all these ideas using 1 or 2 lines logic. For example, in this case, let's try to prove it analytically, all right? So from A divides N, you can write that N is some multiple of A. For example, that integer multiple is Q. And B divides N means it means N is some multiple of B as well. But from the idea above, you can see that M divides AB and M is co-prime to A would mean M must divide the other factor. So N divides A and B also divides N, which means B divides N would just mean B divides AQ. And A, B are co-prime, so B cannot divide A, so B has to divide the other factor, which means B divides Q, which means Q is some multiple of B, for example, MB. Now Q is MB and N is AQ, so put this expression of Q here to get N equals to A times, in place of Q, just write MB. So this can be rearranged as MAB. So you can see that N is a direct multiple of AB, an integer multiple of AB. So N is divisible by AB, we just proved it. And the argument actually used the criteria that AB are co-prime. If this wasn't mentioned, we couldn't argue that B is a divisor of Q. This is the place where the argument would break down, right? Now, here is another interesting idea. Let's write the idea later and let's show you the sketch of the proof first. For example, you have two numbers, A and B, and say the GCD is a number D. Now, you have, from the Euclid's algorithm, you have A equals to some AQ1 plus R1 we are guaranteed to get a pair of Q1 and R1, a unique pair Q1 R1, right? So from here, just make R1 the subject to get, okay, I should have written B here, A minus BQ. Similarly, we had the second equation, B equals to dividing by R1 to get a quotient Q2 and the remainder R2. From here, make R2 the subject to get B minus R1 Q2. And just put the expression of R1 here. So B minus A minus BQ into Q2. Okay, I missed another index 1 here. So let's write a 1 here. So you can see that this becomes B minus A Q2 plus B Q1 Q2 and rearrange to get B times 1 minus Q1 Q2 minus A Q2. So my point is, these are not meaningless calculations. My point is, R is an integer linear combination of A and B, and you should be able to see now that so is R2. R2 is finally an integer linear combination of A and B. We have negative integer coefficient here. The coefficient of A is minus Q2, but it's an integer. Positive or negative doesn't matter, it's an integer. And if you keep going like this, for the third iteration, R3 is actually R2 minus, okay, we have the equation written here. R2 is, okay, R3 is R1 minus R2 Q3. R3 is R1 minus R2 Q3. So you must have R1 here. R1 minus R2 Q3. Now substitute the expression for R2 here. So replace this R2 by this, I mean, this is pretty ugly as an expression, but replace this expression. Finally, and also replace R1. And after both replacement, you should be able to see that since R1 and R2 are both integer linear combinations of A and B, their integer linear combination is going to be again integer linear combination of A and B. The final end result would be an integer linear combination of A and B. This time, the coefficients are going to look even uglier. And if you keep going using the same logic inductively, you can conclude that the final result Rn, which was the GCD, in this case, which is D, this is going to be some integer linear combination of A and B as well. And since we are dealing with integer linear combination, so D can be written as AX plus BY. This X and this Y, they are going to be integers. So the final conclusion that we are drawing from this, all these calculations and logics and arguments is GCD of any two integers, positive integers A and B, can be expressed as some integer linear combination of those two numbers. And this is true for every case. Now, if two numbers are co-prime, their GCD is going to be 1. So special case, when A and B are co-prime, we would find out that A and B can be written inside an equation that looks like this. So basically a linear equation in two variables that has X and Y as a combination, right? So, okay. Now, this idea can be used to formulate problems like this. For example, you can write problem like this, solve to find all, not just pair ordered, all ordered pairs of integers a, b, okay, I forgot to write the equation. So let's write the equation. Solve the equation, for example, 185x plus 395y equals to 1. Now, equations like these, 185x plus 395y equals to 1. Excuse me. All right. So equations like this, where the equation asks you to solve for variables in integers only, not just, if the restriction were to be omitted, then x and y can be, there can be infinitely many x and y, right? You can just put x equals to 1 and find what y is. Y is going to be some fraction, right? Some real number. But if there is a restriction that x and y has to be integers, such equations are called Diophantine equation. For example, x square plus y square equals to 25. This is, if this is a Diophantine equation, you know that 3, 4 is a solution. So is 4, 3, and minus 3, 4, and so on. There can be other solution as well, possibly. So any equation that is restricted to only integer values of the variables is called Diophantine equation. And since this particular example of Diophantine equation is linear in nature, it's called a linear Diophantine equation. Now, we can solve linear Diophantine equations in 2 variables using the fact that we developed here. Apparently, a fact that kind of looked useless, but we can make use of it. We can make actually brilliant uses of it. One of those uses is this one. So how do we solve this? The first thing we do is find the GCD of 185 and 395. What is the GCD? Okay, I think there should be twice of 180's double is 360. We have double of 5 also, so 370. So we must have 25 here. We are using Euclid's algorithm to find the GCD. So 25 times 4 is 100. So 25 times 6 is 150. We have, okay, times, we can go one more time, right? So times 7, we have 150, 175. What am I writing? 175. We have 10 here. So 25 to 25, 10 to 10, and we got our desired zero remainder situation. So the last iteration's divisor is the GCD of 185 and 395. Now, according to okay, let's create let's edit the question a little bit to make it a little easier to solve. So let's, instead of writing 1 on the right hand side, let's change the equation to this. Now you can see that 5 is a divisor of the greatest common divisor of these two numbers. So according to the theorem we just proved in our last page here, we must be able to find two integers x and y, that so that 5 can be expressed as an integer linear combination of 185 and 395 because 5 is their GCD. But we just confirm that there exists such x and y. Otherwise, we could just say that there is no solution, right? So all we did so far is a confirmation that such x and y exists. But what are the values of x and y? What should be the solution? Euclid's algorithm helps here. Basically, 185, 395. So 395 was divided by 185 twice, and the remainder was, what was the remainder? 25. And then 185 was divided by 25. We got 7 here, and the remainder was 10. And 25 was then divided by the last remainder 10. The quotient was 2, and the remainder was 5. And finally, 10 was divided by 5 to get an absolute zero remainder. Now we are going to reverse engineer. So what we do is start with this 5 to write it as 25 minus 10 times 2. Now we are going to replace this 10 by this 10. So 25 minus 10 is going, what is 10 here? 10 is just 185 minus 25 times 7. So 185 minus 25 times 7 overall twice. So we have a 25 here, and 7 times 2 is 14. 2 minuses make it plus. So 14, and we have 15 25s and 2 185s. Now make use of this 25, which is just 395 minus 185 times 2. So 15 times, replace this 25 by 395 minus 185 by times 2, and 2 times 185 here. So we have just 15 395s, and 15 times minus 2 is minus 30. We have minus 2 more 185s. So minus 32 185s. So you can see that this is our x, and this minus 32 is our y, so that this equation becomes 395x plus 185y, and the left hand side was 5. So technically we just showed that 15 comma minus 32 is a solution of the equation 395x plus 185y equals to 5. We made use of Euclid's algorithm to find a pair of values for x and y that satisfies our equation. So technically, we can solve any linear Diophantine equation in 2 variables using Euclid algorithm. You may wonder, what about the situation where we increase the number of variables? Yes, Euclid's algorithm can give us a more generalized method also for solving linear Diophantine equations with number of variables 3 or more. But we are not going to cover that in this lecture or ever in this course actually, because technically you are going to have another level 3 or 4 course on number theory. I took that course last time. I'm not sure who's going to take that course when you get to take the course, but you are going to take the course eventually, and in that course is entirely dedicated to theory of numbers. So these are the introductory discussions of that course, of that 3-credit course. So you are going to get more elaborate discussions on linear Diophantine equations with more variables there. So for now, we are going to just solve linear differential equations of two variables using Euclid's algorithm, the method I just shown, right? Next comes, please let me know if there is any question. Otherwise, I'm going to move on. We have 20 to 25 more minutes, I guess. All right. So, okay. So next thing is a pretty common idea is that it's on prime numbers. So we are going to list a few theorems on numbers, prime, and coprimes. And the first one is every integer, every positive integer has at least one prime divisor. Okay. Every composite, let's not miss the important word here, composite. So every composite positive integer has at least one prime divisor. And this should be evident to you, right? Even this can be said about every prime number as well. The only guy that is weird here is the number one. One is someone who is exceptional. We do not call one a prime number, but at some time there was a debate going on among mathematicians if one is a prime number or not. Now we do not consider one as a prime number, but to me, this is just my personal opinion. To me, one doesn't sound like a composite either. It's kind of it kind of holds a similar position that you can analogously compare to the position of hydrogen in the periodic series, right? It's a bit different. It's a bit weird. Anyway, we do not discuss about one when we discuss topics like what we just wrote here. We skip one for this. Another idea is that you can express any composite number in this form. Some P1, it's one of its prime divisors, but it can be raised up to some highest power. For example, consider 12. It can be written as 2 squared times 3 to the power 1. So I'm talking about a format of this sort. So any composite number can be written as some P1 to the power Q1 times some P2 to the power Q2, Q2. And maybe it has n number of prime divisors. And the idea is all the PIs are different. There is no repetition. And instead of writing this entire expression, we can just write from I equals to 1 to n, pi to the power qy. So this is a form that any composite number can take. And this expression is unique only, if you just do not consider the arrangements differently. If you just write 3 to the power 1 times 2 square, this is also 12. And from this, if you say that, no, I do not believe that this representation is not unique, then you are going to sound funny, right? Because this is just rearrangement. So up to rearrangement, if you consider up to rearrangement, then this expression is going to be unique. It's not possible to express the same composite number in different prime factorization like this. Now, there are some related topics on prime numbers. For example, number of primes is endless. These are pretty simple. Basically, for example, if you the number of prime numbers is infinite. It's not finite, and it's easy to prove. If you consider that there are only finitely many prime numbers, then say you have just n number of prime numbers, multiply all of them and add 1. So you get a number which is bigger than each pi. So this number is greater than each pi. First of all, it's not divisible by any of the pi because this one is going to interfere, right? So if you divide this expression by any of the pi, you are going to get 1 as a remainder. So it's not divisible by any of the pi. So you have a number which is a composite number. And according to the first statement, this first one statement actually looks silly, right? Every composite number has at least one prime divisor. Sometimes some mathematical information looks silly and useless, but generally, in most cases, they are not. For example, in this case, we can make use of this idea in number 1 to prove our last claim that number of prime cannot be finite. You can see that this is a composite number. It must have at least one prime divisor, but unfortunately, none of the PIs qualify for that case because this one is going to interfere in every case. So there has to be some other prime number. And since these are the first few prime numbers, that other prime number is going to be greater than each one of them. Basically, what I mean to write is actually 2 into 3 into 5. Sequentially, the first n prime numbers, I meant that. So none of the first n prime numbers divide this composite number, but there has to be some prime number that divides this guy. So that some prime number must be greater than Tn. So using this logic inductively, we can produce bigger and bigger prime numbers. So the number of prime is not finite. And there are some other ideas in the book. I want you guys to study those by yourself because they're pretty simple. Now let's try to find some interesting parameters related to some integer. For example, if you are given, let's discuss with a problem. Let's consider the number 4200. So let's call this guy n. So my first question is find the number of divisors of n. I have some other questions also. This is one, to find the sum of all divisors of n. I may add some other questions as well. For now, let's solve these two. The first one. How many divisors does the number 4200 have? Let's try to find out the answer. So we have 4200. Let's factorize this guy. It can be written as 2 into 3 into 7 into 100, right? So 100 is also 2 square times 5 square. So we have overall 2 cube times 3 times 5 square times 7. Okay, we're done. So we did not find the number of divisors. We just factorized 4200. How many divisors should 4200 have? Well, write any divisors of 4200 by observing this format. If I say 2 squared times 3 is a divisor of 4200, all of you would agree because 2 squared divides 2 cubed, 3 divides 3. So this guy qualifies as a divisor of 4200. But if I wrote 2 to the power 4 times 3, this would not qualify because even though we have a 3 here, but we do not really have 4 2's in the factorized form of 4200. The highest number of 2's 4200 contains is 3. So you cannot have a power of 2 greater than 3. In fact, these powers are the highest possible powers that any factor of 4200 can contain. So technically, any factor of 4200 should look like this: 2 to the power something times 3 to the power something times 5 to the power something times 7 to the power something. Let's write P, Q, R, and S as the powers. So we now know that P can take values from integer values from 0 to 3 only. Q can take integer values from 0 to 1 only. R can take from 0 to 2. And what about S? S can take from 0 to 1. So each choice of PQRS produces a new factor for 4200. So all you have to do is count the number of choices for PQRS. How many choices for PQRS do we have? You can just use simple permutation combination techniques to get that. How many choices for P are there? It's not 3, it's 4. The 4 choices for P are 0, 1, 2, and 3. So there are 4 choices for P, 2 choices for Q, which is 0 and 1, 3 choices for R, 0, 1, and 2, and 2 choices for S, 0 and 1. So if you multiply these 4 numbers, you will get the final number of divisors of 4200, which is 4 can be written as actually 3 plus 1, 2 can be written as 1 plus 1, 3 can be written as 2 plus 1, and 2 can be written. Why am I writing like this? You can understand that these are just P plus 1, Q plus 1, R plus 1, and S plus 1. And this is not a coincidence. This is going to happen every time, because any whatever the value of the power of a particular prime is, you have one more choices than the power, because you can take 0, that is a certain factor of 4200 may not contain 2 also, right? So in that sense, we just developed that if n is a number which can be expressed like this, then the number of divisors generally there is a standard symbol for this, tau of n. Is it tau of n? I'm not sure if tau is standard, but there is another one which is d of n. So let's write that one. So this would mean the number of divisors of n is okay. There is a mix up of n here. So let's write k as the highest index. So number of divisors of n is going to look like this: product of the powers qi plus 1, I equals to 1 to k. So this works like a formula, right? Please let me know if there is any confusion here in the solution process of problem number 1. All right. What about 2? 1 was in a way easy. You just had to solve it. We converted it into a permutation problem and solve the permutation problem. That's all. What about number 2? We have to find the sum of all divisors. So technically, for 2, we have our n is product of pi to the power qi. I runs from 1 to k. So now we want to find the sum of divisors is probably expressed as S of n, even if it's not. Let me use it for this particular solution. So Sn stands for sum of divisors for this problem. So Sn is just sum of every divisor, and any divisor of our number is going to look like this. Just using the logic for 4200, any divisor, this is a divisor, this is not. So this is the format of any divisor, right? So any divisor is going to have the format pi to the power some power. But what is the power? Say the power is denoted by ti, where I runs from 1 to k. But the TIs can vary from 0 to QI. So all possible combinations of TIs from 0 to QI. So this is one of the divisors. Now we are going to sum all possible divisors where TI runs from 0 to QI. Now, technically, we can just do this, write the product here, and sum here, pi to the power ti. Now, this sum for index I, it was not a very easy series to solve, but here the summation variable is not I but ti, and for ti this sequence you should understand we have pi to the power 0 plus pi to the power 1 plus pi to the power 2 up to pi to the power ti. So for the summation variable ti, this is just a geometric progression, right? And what is the sum of this geometric progression? Pi to the power ti plus 1 minus 1 by pi minus 1. And this is a very old formula. You have been using this for a long time now. So I equals to 1 to k. We have pi to the power ti plus 1 minus 1 divided by pi minus 1. So you can use this as a formula for sum of divisors. So for 4200, we have the product of how many PIs are there? 4, 2, 3, 5, and 7. So for 2, it looks like 2 to the power. We have to increase the power by 1, right? So 2 has power 3 here. So 2 to the power 4 minus 1 by 2 minus 1 times the second factor is 3, the power was 1. So we increase 1 by 1 times the third factor was 5. 5 had power 2. So we have to write 5 cube minus 1 by 5 minus 1. And finally, 7 had power 1. So 7 square minus 1 by 7 minus 1. All you have to do is complete this multiplication to get a complete answer. And that's all. So this is how we find the sum of all divisors. Next comes, let me add a third question here. The number of ways in which n can be expressed as the product of two factors which are prime to each other. Let me know if the question was not clear to you. The question asks to find the number of ways you can arrange or rewrite n as a product of two factors, but there is a catch, there is a condition. The two products has to be co-prime to each other. So technically, you can see that, so to solve number 3, let's try to delve deeper into the question to understand the question better. 4200 can be written as 42 times 100, but this is not acceptable according to the description of question number 3 because 42 and 100 are not co-prime to each other. But if you wrote 2 cube times 525. 525 is nothing but 3 times 5 squared times 7. So if I have not made a mistake actually. I think I'm correct. If I'm not, please consider the idea only and not the numerical values. So basically 2 cube and 525 are co-prime to each other. I made sure by just, you can see that 4200 was written in this form, right? 2 cube times 3 times 5 square times 7. So to make sure that your partition of the two factors are co-prime to each other, all you have to do is rearrange them into two boxes. Just make sure that you do not have any of the 4 prime numbers common anywhere. So if you take 2 here, just take all of the 2's you have. Do not leave behind any of the 2's. If you write 5 here, take all of the 5's. And after filling up the first box, write all those remaining in the second box. So we have 3 here and 7 here. This is how we can make sure that the partition are co-prime to each other, right? So how many such representations are there of 4200? This is the question asking. I hope the question is clear to you. If it is not, please let me know. Otherwise, I'm moving forward with the solution. Now, say our number n, the same old representation, summation I is from 1 to k, pi to the power q. Now, consider an expression 1 plus p1 to the power q1 times 1 plus p2 to the power q2 and so on up to 1 plus pn to the power qn. Basically, we are considering the expression product of from I goes from 1 to not really n but k, right? 1 plus pi to the power qi. Okay. Let's consider a smaller case to let me explain in an easier way. Let's consider that n is just p to the power p1 to the power q1 times p2 to the power q2. Let's consider the case where we have just two prime factors. So the expression we just considered then becomes a smaller one, 1 plus p1 to the power q1, 1 plus p2 to the power q2. If you complete the multiplication, what you get is 1 plus p1 to the power q1 plus p2 to the power q2 plus p1 to the power q1 times p2 to the power q2. My claim is the idea was, the governing idea here was, if you take to forget the second box, if you complete the first box, the second box becomes an automatic choice, right? The remaining, all the remaining numbers are going to put in second box automatically. So all that matters is choice of first box. So in the first box, if you take 2, you have to take all of the 2's available. So take the highest power of 2 here. You cannot take 2 square or 2 to the power 1 here. You cannot take 5 to the power 1 here. If you are going to take a pi, take the highest power of pi. That's the idea. So in this case, if I want to make a possible partition in the first box, if I want to take p1, I have to take q1 as its power, and the remaining guys are going to be in the second box. Again, if I going to if I am going to take P2, I have to take Q2, remaining everything going here. Another choice is taking P1 and Q1, P2 both, then taking Q1 and Q2 as their powers. There was no choice of power here, and remaining just 1 in the last box. In this box, you have P2 to the power Q2. In this box, you have P1 to the power Q1. So focusing on the first boxes, these are the choices where you took. There's one choice remaining. You could write 1 here. Then the second box would contain P1 to the power Q1, P2 to the power Q2. So forget the last box. In the first box, your choices, you have 4 choices here, right? So where did the 4 come from? You should be able to see that the choices in the first box are exactly these 4 guys. And who are these 4 guys? They are the terms in the expansion of this product. And this is going to happen even for bigger number of prime factors also. If you had other prime factors, as for example, if you had P3 to the power Q3 here, all you had to do is add 1 plus P3 to the power Q3. When you multiply, you get different combinations of the terms where each term is going to contain all the powers of the prime factors it includes, because I made sure of that here. That is why when you multiply these 3, you'd get 2 cube. Here you got product of 2 terms. So this is just 2 square. If you multiply all 3 here, you'd get how many terms? 2 cube number of terms. So 8 terms. But what are the number of partitions? You should be able to see that there are repetition of partitions. This guy and this guy is actually same. Also, this guy and this guy is also same. So you have to take half of the number of terms in the expansion of the products. So divide 2 cube by 2 in this case, divide 2 square by 2 in this case. So if you have, in our case, now how many products are here? Exactly equal to the number of prime factors here. How many prime factors our number had? In general situation, we had k number of prime factors. So the number of such representations should be 2 to the power k divided by a 2, because there were repetitions. So dividing by 2, we would get 2 to the power k minus 1. So in case of 4200, we had how many terms? How many prime factors? 2, 3, 5, and 7, 4. So 2 to the power 4, but I have to reduce the 4 by 1 because I have to take half of this, the combinations because of the repetition. So overall, 8 number of factorizations possible into 2 factors, where the 2 factors are going to be 4 prime. Please let me know if this was clear to you. All right. If there is no question, okay, it's already 3:28, so I think I have to close here. So let me is there any question from anywhere on today's lecture?
Has the chapter
not-
finished?
Sorry?
Chapter is finished, right? Finished.
No, the chapter is not finished. We are going to continue from where we left today
Okay.
in our next class. All right. So if there is no more questions, I'm going to stop the recording. I need to discuss something with you in a minute. Let me stop the recording.